Okay, this is a short video lecture on inverse functions, which is covered in section 11.1 in your text. This would be suitable for Wednesday's test, and obviously there'll be some questions like this on the exam. Our exam review is going to be on Thursday and Friday. Okay, so here's the first idea. Find the functional inverse of this function f of x is 3x minus 1. The functional inverse is denoted in special notation. We use f inverse of x. And the idea here now is that we want this function that we know, 3x minus 1, and this function here that we don't know to undo each other. F inverse has to undo what f does. And so a couple of examples. If I put 10 into f, this would be 3 times 10 minus 1, which is 30 minus 1, which is 29. Okay, so f of 10 is 29. If I have the correct f inverse, it has to undo this. So if I put 29 into f inverse, I'm supposed to get 10. That's the idea. Okay, so again, how do I find f inverse? Okay, there is a 3-step recipe. So 3-step procedure if you want. Recipe or procedure. The first thing is to write f of x is 3x minus 1 using y in place of f of x. So here's our first step. Y equals 3x minus 1. Done. Okay, second step. Swap x and y. So what we're going to do is we're going to change places with the x and the y. We're going to write that equation down now. X is equal to 3y minus 1. And so that's the second step. We've done that. Okay, and the third step now is to solve for y. So we're going to take this blue equation, x is 3y minus 1, try to get the y by itself. Not hard to do. Add 1 to both sides. X plus 1 is 3y. And lastly, divide by 3. So y would be x plus 1 divided by 3. This is now going to be our inverse function, and we can use the special notation for inverse functions. F inverse is going to be x plus 1 over 3. There is a note in your text, a caution that we should probably reiterate here. This is not an exponent. It looks like an exponent. It's a little number up in the air, but in particular, F inverse is the way we read this, does not equal 1 over. If that really were an exponent, you know, -1 exponent means you just do 1 over. This is not an exponent. It's sort of unfortunate that we have that notation there, but that's what's used in mathematics. F inverse is denoted with a little -1 up in the air. Okay, so let's see how this actually comes into play. Remember our function that we had up at the top was 3x minus 1 here, and we wanted to come up with a inverse function that would undo this. And after going through this process, we have found that F inverse is equal to F inverse of x was equal to x plus 1 over 3. And just to double check to see whether this worked, we put 10 into x for f, right? And we got 29 out. So if we want to undo that, f inverse of 29 is going to be 29 plus 1 over 3, which is 30 over 3, which sure enough is 10. Okay, so we found a function that undoes that. Not terribly hard to do. As a second example, let's pull up another page here, and let's find the function f inverse that undoes the exponential function f of x is 2 to the x. Okay, so we need some function that undoes this. Let's follow our three-step recipe. Step one is we write this using y in place of f of x. So y is 2 to the x. And by the way, a short sketch on this. This is an interesting function. It's the exponential growth function. The curve grows pretty quickly. You could put some points in. You would find there'd be a 0.01. There'd be another 0.12. There'd be a third 0.24. Another point sticking up here might be 3 and 8. Okay. In the negative direction, there'd be a point here, -1, -1, Joe, -1 and 1/2. And you could verify that all of these points lie on this exponential doubling graph. Grows very, very quickly, goes off to the right here. And as we go to the left, the curve gets really close to the x-axis, but never hits it. Okay, so we're trying to find a function that undoes this. And we've done our first step. Now, remember the second step is to swap places of x and y. So we have x is equal to 2 to the y. And now our third step is to solve. So we have to solve for y. That's what we have to do. We have to get the y by itself. Now, this is a rather intriguing equation. How do you get the y by itself? And you go, well, geez, I don't know. I'm not dividing by 2 because this does not say 2 times y. It's not a multiplication process. It's an exponential process. So the way that we're going to solve that is to resort to our Rosetta Stone. We know that 10 squared is 100. That's an exponential form. Is the same as log base 10 of 100 is 2. So if we sort of match this equation up with this, we see, let's see, I have 2 to the y is equal to x. And again, I've sort of swapped around the equal sign here. I know I can do that. 2 to the y, x is equal to 2 to the y is the same as 2 to the y is equal to x. And the reason I did that was because now you can easily match up. 2 is going to be the base. 2 is the base, and that's going to be the base of our logarithm over here. So we have log base 2. The exponent is y. That's going to be the exponent here. That becomes the value of the logarithm. So over here we're going to get y. And I suppose I should probably go ahead and write this one in blue as well. So there's the base. And the argument of the logarithm, this 100, I better not use red, Joe. Let's see if we can, we'll put black there. So the argument of the logarithm is the same as the value of the exponential, and that matches up with x here. So we have x. Okay, and in fact, we've solved for x. This equation is exactly the same as this equation. And they're not equal, but they're equivalent equations. So solve for y, we've done that. Yeah, I said solve for x. We're solving for y, obviously. So we now know that y is equal to log base 2 of x. And because we're finding inverse, we can now use our inverse notation if you want, log base 2 of x. Okay, so here's our, let's back up just a little bit. Here's our function, the exponential function, 2 to the x. And we have found now through this little process, we have found the inverse function, which is the logarithmic function using base 2. Okay. Now, one more idea before we jump into the book. Not all functions have inverses. Okay, so to make or to have a function be invertible, to have a function that is invertible, it must be 1 to 1. Or another way of saying that is pass the horizontal line test. Okay, so a couple quick sketches, and then we're going to stop this video here and do another short little segment on this idea of invertible functions and horizontal line tests. The first function we dealt with was y is equal to 3x minus 1. This is a line with slope 3, y-intercept of -1, and this line is a function, right, is a function. It does pass the vertical line test. All functions pass the vertical line test way back in chapter 2, and I'll give you a page reference in the other video. Okay, but in addition to vertical line test, this function is a special type. It passes a horizontal line test. So imagine a horizontal line moved anywhere, and this horizontal line will hit the function only in one spot. So yes, this function is 1 to 1, 1 to 1, and so it's invertible. It does have an inverse. Remember, the inverse that we found was x plus 1 over 3. So we did that. And likewise, when we looked at our growth function, let's get a little sketch of that going. The growth function was this guy here, this exponential growth. And again, it passes both a vertical line test, all functions pass that, okay, but also passes a horizontal line test. So imagine a horizontal line moving around, and it will hit this only in one spot. Okay, so this is a 1-to-1 function, 1 to 1, and hence this is invertible, and it does have an inverse, and we found the inverse. Here was our function, was 2 to the x, and the inverse that we found just earlier in this video, f inverse, was log base 2 of x. They undo each other. Okay, for further reference, you should go ahead and jump into your book. All of this is in the very first section of 11.1. And another video will go ahead and elaborate on all of these just a bit more. Let me stop this right here.